Welcome to this webinar given by Integrate and Abstract Solutions on the subject of requirements and model-driven engineering. Just so that you can put a face to the two presenters today, I have put a picture of us both there. I am Jeremy Dick from Integrate, and later on you will hear Ian Wilkie of Abstract talking to you. Just a note to say that this webinar is being recorded, and so we would encourage you to pose questions through the chat line, and we will pick them up at the end and respond as best we can. The purpose of today's webinar is to introduce concepts around which the requirements process and the modeling process can be understood as complementary techniques. So we're not talking today about tools, we are talking process and concepts and how these two processes can mesh together for useful purposes. We hope that in future webinars and workshops we will be able to interest you more in the tools that support these two processes. So what I'm going to do to start with is just present some of the basic practices and principles of the requirements process. And that will equip us to understand the relationship between requirements and modeling. And we'll talk a little bit about the role of modeling before drawing some conclusions. So, the basic principles of requirements. The first principle or practice that I want to talk about is this idea that we manage requirements in layers. Now, it doesn't really matter what you call the layers. The example on the screen is one organization's name for 3 layers of requirements, and it doesn't really matter how many layers you have. The number of layers you have will reflect the complexity of what you're developing and the contractual context in which you are developing it. But the idea of developing requirements in layers is to give us a systematic framework for the development of the requirements in line with the design. And one of the principles that we try to apply at each layer is to get the appropriate degree of agnosticism with the design. You want to be design agnostic at the top level, in other words, to capture the set of requirements that contain no design, no solution details at all. And then the next layer down, we can introduce a layer of solution and add a bit of detail, and the next layer down, we can add more details of the solution, and so on and so forth. So we manage the requirements in layers as a means of managing the complexity of what we're developing. The next principle is that we express our requirements concisely as single-sentence shell statements. So rather than thinking like a novelist and writing flowery paragraphs, we think as an engineer and write these concise, atomized requirements. And there's a whole discipline around how these should be written. And the subject of these sentences reflects the level at which the requirement is written. So whilst at the top level we're talking about, for instance, the whole plant, then the subject is the plant shell. And then at the next level down, when we have decomposed the plant into areas, functional areas, we might then start the requirement with the functional area shell, and so on and so forth. The third principle is that we capture the relationships between requirements across the layers. So as we write in the example on the screen our design basis requirements, we are writing them in response to the higher level requirements in the functional specification. So let's capture that relationship. Likewise, as we write our system requirements in this example, we are responding and satisfying the requirements from the layer above. So we can characterize that relationship as the satisfaction relationship or the satisfies relationship. And this is an example of requirements traceability, which lies at the heart of requirements management. There are other relationships that we might capture and as well, and this slide shows a relationship between the design and the requirements. Now, the principle showed on this slide, though, is really that rather than just tracing requirements to requirements, we capture also rationale to explain the relationship. And this is where design and models link into the requirements process, in that they are supporting the rationale for the decomposition of the requirements. And we can characterize that relationship between the design and the requirements as a supports relationship. Now, here are some examples of what I mean by this rationale. Here's an example that talks about a pacemaker. The pacemaker should ensure that the heart beats safely at a minimum rate set by the physician. And we've chosen, at the next level of requirements down, to decompose that requirement into 4 functional requirements. But in the middle, we capture what we've called here a satisfaction statement, which is a bit of narrative that explains the relationship and why we decompose the requirement in that way. We're not writing a requirement when we write that satisfaction statement. So instead of it being a single sentence shall statement, we can be much more free with the narrative that we provide. It is useful, though, to start that statement by saying, this requirement is satisfied by, because that focuses on the fact that we're not writing a requirement, we are capturing rationale. Here's another example to do with engine management software. And again, we decompose a requirement at a high level or lower level requirements. And it may not be immediately obvious from those lower level requirements what the design intent is. So we capture a paragraph of text that describes that design intent. And now we can read the high level requirement, we can read the rationale, and we can read the low level requirements, and we can say, ah, yes, I understand what's going on here. Now, as we decompose requirements, there are a number of things going on. One of the things that's going on is that we might simply be allocating function into a subsystem or a component of our design. The other thing that may be going on is that there's a genuine transformation of a requirement in a more complex way into the solution. And this example shows both of those. The ambulance controller shall be able to transmit incident details to the ambulance driver. It's the function that's being described here, or the capability. And that is allocated as a function on the communication system, which is going to allow this to happen. So that's an example of allocation. But the second bit of that high-level requirement, with an availability higher than 95%, is transformed in the solution into a mean time between failure and a mean time to repair. And there's an arithmetic relationship between those low-level requirements and the high-level requirement. And somebody has done the arithmetic and determined that that MTBF and MTTR will give us the required availability. And we're going to see that our models are going to help us to frame that kind of requirements decomposition between the layers. So let's go on now to talk about requirements and modeling. You will see here represented what's sometimes called the systems engineering sandwich. This came out of a presentation to INCOSE back in 2002, I believe, and is intended to describe the relationship between requirements and modeling and design. And the bread in this club sandwich is meant to represent the layers of requirements, and the design and modeling activities is the filling in the sandwich that allows us to move from one layer of requirements to the next, and then from that layer to the next, systematically introducing the design of the solution. Another way of looking at this is to view this as what is sometimes called the Z model. let's have a look at what the Z model is. Down the left-hand side of this screen, we have our layers of requirements with the satisfaction relationship between them. Now, typically what will happen is we may have some statement of need that may not be a formally expressed set of requirements at all, but in response to that need, we will do some modeling. And the nature of that modeling may be some goal analysis, maybe some user stories, use cases, and through the use of that kind of high-level modeling, we will attempt better to understand the problem to be solved, and from that modeling derive our first formal expression of requirements. Perhaps we'll call those the stakeholder requirements. So we can see how modeling has been used to derive a layer of requirements. Once we have our new layer, we can repeat the process. We'll do more modeling. The modeling may be different in nature now. Maybe we're getting into functional modeling and analysis. And here we will determine perhaps what the best architecture for the system is going to be that will meet the stakeholder requirements. And after we've done that further modeling and analysis, we will be able to derive the system requirement, and so on and so forth. And as we go down into the design, the nature of the modeling will become different and more detailed and focused on the nature of the design. And so it is this zigzagging between the requirements and the modeling that leads us to call this the Z model. Now, behind the Z model is this idea that modeling informs the requirements flow down. So in fact, if we look at the relationships between these layers, what the modeling and design is really doing is informing the way that requirements are decomposed. It's also informing the structure of those requirements at the next level down. It's clear also, by the way, that the modeling should be driven by the requirements as well. So there is this give and take between the two sides of this slide. The modeling is driven by the requirements, but once the analysis is being carried out through the modeling, we're able to inform the way the requirements are decomposed to the next level. So let's take an example. Suppose we have some stakeholder requirements. Now, in systems engineering terms, one of the first things that we'll do is to draw what's called a boundary diagram. And this is indeed a form of modeling at a very high level. We will take, in this particular example, we're developing a waste processing plant. We'll take the whole plant as a black box, and we will examine what sits at the boundary, what the inputs are, what the outputs are, what the control interfaces are, and we will talk about what the waste processing plant has to do functionally to its inputs to produce the outputs without yet talking about a particular solution. That is the discipline. And once we've done that, gone through that exercise, we may well be ready to write our next layer of requirements that express that, more formally, that function of the black box, which we've called the waste processing plant. Now, subsequently, for the next layer down, we're going to open up that black box of the waste processing plant. Here it is. And we're going to do our first layer of design, which is to say that plant is going to consist of a number of systems, if you like. We're going to have a waste receipt unit, a waste sorting unit, a waste packaging unit, a dispatch unit, etc. With that top level of architecture comes in internal interfaces. And each of those subsystems becomes a black box, and there will be a set of requirements describing what each of those black boxes are supposed to do functionally with their inputs and outputs. And once we've gone through that exercise, that level of modeling and analysis informs the way the requirements are decomposed at the next level down. So suddenly our system becomes a set of subsystems, and the requirements of those subsystems work together to satisfy the requirements at the system level. And now this process repeats itself. We can pick up one of those black boxes, for instance, the waste packaging unit, and we can open that up. So there it is as a black box with its inputs and outputs. We open it up, and we determine that inside there we're going to have a waste chute, a package stand, a sealing machine, and a package storage area as subsystems or components. And each of those is a black box, but they interoperate together within the waste packaging unit to achieve the required function. So if we look at what's going on here, you can see the recursive decomposition of the system into smaller and smaller units. And that model, again, informs the decomposition of requirements from the waste packaging unit into its components. So you can see here how this Z model operates in a way, as we do some analysis and modeling and design work, and that helps us derive a set of layer of requirements, which then leads on to further analysis and modeling, back to the requirements and so forth. What's really going on here is that we are effecting layer by layer the transformation of a true set of requirements into a set of detailed specifications. Now the thing about requirements is that they are supposed to permit multiple possible solutions, and the requirements are what should pertain to any solution that you propose. Whereas specifications are specific to a particular solution, included in the name, a specification. And if you will permit me a little play on words with the name of abstract solutions, we are moving from something that is abstract, and thus permitting multiple solutions, into something that is a specific solution. And the requirements process, presented as layers in this way, provides a systematic framework for performing that decomposition down through layers of design and down through your gated process. So now we're going to talk a little about the role of modeling, and I'm going to hand over to Ian now, who will address the next few slides. Ian.
Okay, Jeremy, thank you very much. So if we could move on to the slide on the role of modeling. What do we use modeling for? Well, a number of different things. Primarily, we're using it as a route towards understanding the problem that has been set to us by the requirements and moving towards a solution, moving towards an implementation. And doing that in a way that uses the abstractions of modeling to help us analyze and understand complex subject matters that we have to deal with in building typical systems. The model can both help us understand the subject matter, but then also provide an architectural framework for the implementation. And used with an appropriate process, it can form the central focus for the development of the solution. It can also, of course, be used to communicate with stakeholders to validate the requirements. In particular, as we develop models, questions are going to come up, and we will want to get answers to those questions about how things should behave in particular circumstances, get answers to questions that may not have been covered in the original requirements. And finally, the models will provide a framework that help us verify the solution that we've created. So, if we could move to the next slide, please. What I'm going to show in this slide is an example of the kind of model that we might build, and this is going to build up in a number of layers, as you see, a decomposition from a component model to a class model, and then finally we're going to see how a state machine will represent the behavior of a particular entity within the class model. Now, an important thing to realize is that there are different modeling techniques that might be used for different purposes at different layers in the Z model that Jeremy talked about. So we might use modeling at a very high level, at the system level, where we will create models that show the interaction between the system and the environment and explore some aspects of the behavior at that level. We might then move down, considering the system as multiple components, some of the components of which are going to be implemented as hardware or are going to be pre-existing off-the-shelf hardware, and other components which are going to be implemented as software in a control system and so on. And then finally, we might use modeling at the level of implementing and understanding and implementing each of those components. So there are many different kinds of models we could build, and there are many different languages that we might use to build them in. What I'm going to talk about a lot in the next couple of slides is one particular modeling language, which is UML, the Unified Modeling Language, which we can use both for system-level functional modeling through SysML and software-level modeling with UML. And the model that's shown here is one that might be typically constructed for a control component of a larger system. In fact, this particular example is concerned with managing all of the equipment that's used on an aircraft, so all of the equipment, navigation, weapons systems, power systems, and so on. And this would be a typical software-oriented model. What kind of things can we do with the model? Well, we can use them as a way of understanding complex subject matters. So in this particular model, we move from a component-based architecture at the top level through a breakdown in terms of classes down to state models which specify behavior. And those models are very much focused on the problem domain. So you'll see that if you look in the middle, look at the classes, there are terms and terminology which is probably going to be understood by the subject matter experts. It talks about weapons and downward-facing weapons, forward-facing weapons, downward-ejected weapons, and so on, weapons of different types. And the behavior will talk about things that the subject matter experts will understand. And we can use these models as a way of understanding the problem and teasing out things that we may not have found in the requirements before. So we might have had a requirement that said a weapon cannot be ejected, a wing-carried weapon cannot be ejected when the aircraft is flying upside down, because then there's a severe risk to the aircraft. And as we build the model of the precise behavior that works that out and controls that, questions will occur to us such as, well, what happens if the aircraft is rolling at the time and there is a chance that between starting the eject sequence and completing it, the aircraft will become upside down. So that will raise a question, and that will, as Jeremy described, feed back in and inform the requirements at that level in the system. And we'll have to clarify those requirements with subject matter experts to understand them. The modeling can also be used as a way of structuring the solution, and in particular, we very much favor a style of modeling which gives us a component-based architecture. So at the top, we describe the system in terms of a number of components, and we organize those components for particular qualities. So for separation of concerns, for portability to ease the long-term maintenance of a system, and also for reusability. In particular, very often what companies want to do is support a number of different product lines that are all very similar. And we can use that modeling to support that idea. So there are a number of different things that come out of there: understanding the subject matter, creating an architectural framework which gives us long-term maintainability of the system, and of course all the while linking back to the requirements, and I'll talk more about that in a second. So if we could move to the next slide, please, Jeremy. Such models are delivered as part of a process. We're not just sketching a few diagrams on pieces of paper. What we're doing is that we're building a set of deliverables that are core to the development process through a series of model artifacts. And in this particular example here, we do it by going from use cases through to the component-based architecture that we call domains, through to interaction models that show the interactions between the components, And then for each of these components, we'd create a model that describes the classes representing the entities in the problem domain and the relationships between them, and the behavior of those classes in terms of state machines. Hopefully this slide is going to build up in a second and show that. There it is. And then the detailed behavior in terms of actions. Now, it's important to note that this process can be iterative, and we'll see on the next slide how that works in more detail. But it can be iterative, so we can have iterative development where we deliver functionality piece by piece in an agile-like way, supporting continuous integration. But nevertheless, the process is formal and rigorous so that we all know what we're building and we know when we've built it successfully. And so modeling, instead of becoming an afterthought with some diagrams that are sketched on pieces of paper, becomes the core of the development process, from which we can develop, we can generate other artifacts. So, for example, information exchange requirements, system documentation, and so on. And ultimately, even the code, if we build the right kinds of models and we have the right kind of tooling. So we'll build these models as part of a defined process. And the next slide will show us how that process typically links back into the requirements at any level. So if we could move to the next slide, please, Jeremy. Thank you. So typically we'll start with the requirements at a given level. And from those requirements, we'll group them together in functional areas, which will be represented by a use case model. We'll then do some interaction modeling, as you see in the top left there. And from that, we'll feed those interaction models into the component-based architecture. And each of the components will be further elicited as a class-based model supported by a state machine that's in the center of the diagram, or supported by many state machines. And with the right tools, we'll be able to execute those models. Now, as we go around that loop on the left-hand side and down the middle of the slides there, as we build the models, questions will come up that will relate back to the requirements that we started from, and therefore potentially raise new requirements or clarify existing requirements. And ultimately, as we reach down to executing the models, we will then see whether the models that we've created meet the requirements that we started from in the first place. So we have a continuous iterative loop of development at each stage, linking back to and understanding the requirements and further informing our understanding of those requirements. And finally, with the right kind of tooling, not only can we go around this loop and execute the models for the purposes of simulation and understanding, but we can also, if required, generate the code, generate implementation. Now, as I said, different models at different levels of in the process for different purposes, but typically if we're doing this at the level of a component that is implemented by software, then we'll be able to do that. So that's an example of how we typically can use modeling at different levels in the process. Models both driven from and feedback, providing feedback to the requirements as we use the modeling abstractions to formalize and capture the totality of the requirements into a coherent model and realize that there are potentially gaps or misunderstandings or confusions in the requirements that we can then get clarified and feedback into the requirements process. So at this point, I'll hand you back to Jeremy.
Thanks very much, Ian. So what we are trying to promote in this webinar is the idea that the requirements process and the modeling process are complementary. On the requirements side, the discipline is about capture of requirements and the systematic decomposition of those requirements through the layers and capturing the traceability. And on the modeling side, we are dealing with structuring information in particular ways and viewing it from multiple angles, learning things about the structures and the solutions and checking things, consistency checking, not just through a common vocabulary, but also through the consistency of the structures that are built. And through the modeling also because of the formality of the structures we build, we've got the possibility of this execution of the model or animation of the model to check that it has the right behavior. Now, one of the things I like about these two disciplines is that as you apply the requirements discipline, it encourages you to ask certain questions, like where does this requirement come from? What is it serving to satisfy in terms of the customer's views? And modeling also encourages you to ask certain questions about the structures that are being built and the language of the model, etc., etc. And so the questions that they encourage you to ask are also complementary. I would like to state a note of caution, though, that the model on its own will never contain the complete set of requirements, or very rarely. And this is because the models that we use are not able formally in their notation to capture all types of requirements. The non-functional requirements in particular may never be captured in your model, which means you need the ability to retain textual requirements just to capture those requirements. Another concern is that certainly in the cultural environment of today, customers find it hard to sign up to a model. Contractually, they find it much easier to sign up to a set of textual requirements. However, it is true that, especially if you're developing software, you can create a model from which you can generate code. So there is a sense in which that model does capture everything you need, all of the requirements, if you like, to generate a solution. But how often do we develop software entirely in isolation from a wider system? And so that just emphasizes the idea that actually there is advantage in working these two processes in parallel and in conjunction. So we've reached the point where we're going to draw some conclusions from what we have presented. And really what we've been talking about in this webinar is the combination of requirements-driven modeling and model-driven requirements. Now, if we drive our models from a set of requirements, then we are ensuring that the models are relevant and are addressing the right problem at each level. On the other hand, if we drive our requirements from the modeling, then we have additional techniques for checking that the requirements are complete and consistent. And we've got that additional ability to ask the right kinds of questions to ensure that our requirements are so. It's worth pointing out that today there are really good integrated tool sets that are available that help you support these two processes in conjunction with one another. But that's going to be the subject of another workshop and webinar. And on that subject, what we'd like to invite you to do is to contact us and tell us that if you were able to attend such a workshop, what would you like to see in it? We have a date to propose, April the 28th at IBM Warwick, and we would like to focus that workshop on the things that are most pertinent to your needs. So please let us hear from you on that subject, and we will endeavor to put together an event that will help you advance in this subject. Certainly one of the things we're going to be doing at that workshop is talking about tools and tool support and how requirements and modeling tools can work together. So thank you for listening. We have collected some questions in the process of this webinar, which we are now going to address. And I'd just like to say that if there are further questions that you wish to ask us following the webinar, then please do so using our two emails that are listed there. So the questions that we've collected are as follows. The first question relates to the fact that the latest versions of UML and SysML do permit the inclusion of textual requirements in the model, where you can effectively show a requirement as a piece of text linked to elements of the model. And that is true. So indeed, UML and SysML even have a diagram called a requirements diagram, which allows you to capture what are nothing more formal than pieces of text which contain requirements and the relationships between them, whatever you choose those relationships to be. However, what the requirements process does in this arena that perhaps modeling doesn't do is to place sets of requirements systematically into some context, into some structure. So you will have requirements documents with a complete narrative that you can read and understand requirements in the context that they sit in, which is different from the context in which they sit in a model. So really, how the requirements tool and the modeling tool interact in this way is the key here. But can we actually permit requirements that sit in the requirements tool then to appear in the modeling tool as a linked text box in a requirements diagram style? So it's a really good point, and thank you for raising it. It is a point of overlap between the two worlds.
Yes, indeed. If I might add there, we might certainly want to place requirements on model diagrams for a number of purposes. So, for example, simply for the purposes of illustration, to illustrate the requirement that gave rise to a particular model construct, so that we understand why the model looks the way it does. Or we might indeed want to put non-functional requirements into the model so that the people building the model are aware of those non-functional requirements, for example, performance requirements, which they then use to inform the design process, the modeling process itself, so that they are aware of inefficiencies that have to be eliminated and so on. And as Jeremy says, the key thing is that appropriate tools will enable those requirements in the modeling tool to be integrated with those requirements in the dedicated requirements tool, so that we're not maintaining the same information in more than one place. And indeed, as we do things such as in the modeling tool, linking a requirement to a model element to show that the model element is there because of the requirement, that actually tells us that in some sense the requirement has been satisfied by the model element, and that can be fed back, again, with appropriate tooling to the requirements database itself.
Very good. So here's another question, if I may quote. I'm not really developing software, so how useful are these models really to me? And I think I'll let Ian answer that one first.
Okay, well, as I said, modeling can be used for a number of different purposes, a number of different levels in the hierarchy, and also for a number of different problem domains. The model I showed, of course, is very much focused on software. But nevertheless, even if we're developing hardware, for example, some mechanical piece of hardware or some piece of electronics that has a particular piece of functionality, then nevertheless the model may still be useful for understanding that functionality and fully specifying that functionality through the use of the modeling abstractions. We might then put the model on one side and use it simply as a specification for the implementation. Now, that would be appropriate with a UML model if we were dealing with a subject matter that was particularly focused on functional behavior with systems that have state, for example, and respond in different ways to state and process data on the basis of that. Other types of subject area within the context of building an overall system might have different characteristics. So we might be focusing on, for example, some kind of feedback control loop, or some signal processing problem. Now, in those cases, UML modeling is possibly not what you want to use. It doesn't provide the kind of abstractions that help you understand the problem domain. For those more mathematical modeling techniques, such as those supported by tools like MATLAB Simulink, would be appropriate. The key is we'd use the appropriate modeling technique for the appropriate subject matter and the appropriate domain. However, the broad issues still apply, that we create the model within the context of the overall engineering process, and at any stage the model will link back to the requirements that gave rise to it, and through the use of the model we might well recognize the need for clarification of requirements, or indeed raising new requirements.
Yes, thanks very much, Ian. And I think it's worth also just for a moment taking a much broader view of what a model is here, because each engineering discipline tends to have quite a wide range of analysis techniques that they use. For instance, if you use a wind tunnel to test the aerodynamic properties of a vehicle, that is a form of analysis and modeling. You actually build a scale model of the vehicle and put it into the tunnel to answer certain questions about the design. And that is equally valid as a modeling technique that helps you to decompose a high-level requirement into a set of low-level requirements for a design. So, and there are all kinds of models, there's fluid dynamic model, et cetera, that will be particular to your systems engineering discipline. And they all fit into this framework that we're talking about. Very good. So one last question we have time for, which is as follows. You have portrayed the Z model, where we move from requirements to modeling and back to requirements again. Does this really mean that I have to somehow express the contents of a model again as a set of textual requirements? Well, this is an interesting question as well, pertinent question. And I think that you're absolutely right that in some of the models we create, the information in those models just does not lend itself to be expressed as sets of textual requirements, and it is a bit ridiculous to attempt to do so. And I think that we shouldn't be afraid to write requirements that refer out to the specification of something that occurs in a model. So we might just have a textual requirement that says the structure of this artifact will be as it is, as specified in such and such a model, rather than attempting to reproduce the detail of that model in the requirement set. Ian, what do you think?
Yeah, yes, I agree. It would be tedious in the extreme to attempt to represent every model at every stage by an equivalent set of requirements. And indeed, I think it would be, for many circumstances, an impossibility. Nevertheless, at every level, there is a set of requirements that create the context in which the model has to provide a solution. There may well be more in the solution than there are in the requirements, because there's multiple different ways of solving the same problem. So we wouldn't want to express all of the aspects of that solution as requirements. However, part of the modeling process will very often make us realize that there are requirements that we didn't have that should be there. And so it is useful to produce those requirements and get them written down and get them visible to people, so that everybody understands exactly what the situation is. So, for example, I might build a model of the behavior of control of a petrol pump based on a set of requirements that, for example, specify the typical sequence that a user will go through in order to operate the pump. So we'll have those set of requirements. From that, we create a model. The model will be capable of showing far more elaborate behavior than is indicated by those requirements. So, for example, it will tell us what will happen in all the possible sequences that the user does things in. Now, that would be very tedious to write as requirements, because users, once you get them in the loop, can do all sorts of mischief. Nevertheless, there will be key aspects of that model that will come out. For example, what do we do if the user puts the nozzle back in the pump unit while the system thinks we're still pumping fuel? Now, That may not have been in the original requirement, but clearly there has to be something stated very clearly about that. It's a safety-related requirement, and we need to get that out and in the open and clear and agreed. So that would be an example where one aspect of the behaviour of the model, all of these possible behaviours illustrated in the model, we bring back out as a requirement and get it clear and written down and visible for everybody to see. So not everything will come back out as requirements, but some things will.
Very good. Well, thanks very much. I think we need to close now, but just a final reminder that you will be invited to a follow-up workshop where you will perhaps be able to get your hands on some of the tools that support those requirements and modeling and understand better tool support for these processes as they work together. Please use our emails to communicate if you feel that you would like to have provide feedback or have follow-up questions. Thank you so much for listening, and hope to meet you soon.